Roger, go for launch.
T-minus 3, 2, 1.
Atlas engine ignition.
Liftoff of the United Launch Alliance Delta IV Heavy rocket.
At Space Launch Complex 41, an Atlas V rocket is fueled and ready to launch the third space-based infrared system for the United States Air Force. Good evening and welcome to Cape Canaveral Air Force Station in Florida. I'm Andrea Lenhoff. I'm a parts, materials, and processes engineer focusing on additive manufacturing, also known as 3D printing, at the United Launch Alliance. Tonight I'm joining you in mission control at the Atlas Spaceflight Operations Center. The launch team is not currently working any issues and we're proceeding towards a 7:42 p.m. Eastern liftoff. The launch window for today's opportunity will be 40 minutes. We have already entered a planned 30-minute built-in hold. This hold gives the team time to conduct final systems checks and resolve outstanding issues prior to entering the terminal count. Again, at this point, the team is not working any issues. Later in the show, I'll be joined by First Lieutenant Nick Walton, representing the U.S. Air Force. Lieutenant Walton and I will discuss rockets, SBIRS, and more. And shortly before spacecraft separation, we'll be answering questions previously tweeted about ULA for the rocket and for the spacecraft. Clay Finn, the 45th Space Wing Weather Officer, recently briefed the launch team on the weather conditions here at Cape Canaveral. The probability of violating launch constraints is 0%. The ground winds are 12 knots out of the southwest and the temperature is 76 degrees Fahrenheit. So the weather is within the launch commit criteria and looks favorable for tonight's planned T0 of 7:42 p.m. Eastern Time. Following nearly a 44-minute flight, our Atlas V 401 configuration will deliver the third SBIRS satellite to geosynchronous transfer orbit. Let's take a look at some of the events we can expect to see during today's launch.
The following profile details the important events of this mission using approximate times.
5, 4, 3. We have ignition 2, 1, 0. We have liftoff of the United Launch Alliance Atlas V rocket.
The Atlas V RD-180 main engine ignites to lift the vehicle away from the pad. Shortly after liftoff, Atlas begins its initial pitch, yaw, and roll maneuvers to attain the proper ascent profile and minimize aerodynamic loads. The Atlas V reaches Mach 1, the speed of sound, at 81 seconds. At 91 seconds, the vehicle experiences maximum dynamic pressure. Approaching booster engine cutoff, the Atlas V is burning propellant at a rate of 1,600 pounds per second, traveling at over 10,900 miles per hour, and located 63 miles in altitude and 144 miles downrange. Booster engine cutoff occurs 4 minutes, 3 seconds after liftoff. The booster stage is jettisoned 6 seconds later. 10 seconds after booster separation, the first Centaur main engine start takes place. The payload fairing is jettisoned 8 seconds later. The vehicle now weighs just 8% of what it did at liftoff 4.5 minutes earlier. Cutoff of the Centaur main engine occurs just over 15 minutes after launch. The mission now enters a 10-minute coast phase. At nearly 25 minutes, the Centaur main engine is restarted. This burn will last just over 3 minutes. Following the second Centaur main engine cutoff at 28 minutes 38 seconds, the mission enters a final 15-minute coast phase. At 43 minutes 48 seconds, Centaur releases the third SBIRS GEO satellite for the United States Air Force, providing early missile warning detection.
ULA is using the Atlas V 401 configuration to launch the third SBIRS GEO Flight. This is the 69th Atlas V launch and the 116th ULA mission, as well as the 34th launch of the Atlas V 401 configuration. Produced in Decatur, Alabama and Harlingen, Texas, the Atlas V 401 is comprised of a Common Core booster powered by an RD-180 engine and a Centaur second stage powered by the Aerojet Rocketdyne RL-10C1 engine. The SBIRS satellite is encapsulated within a 4-meter diameter payload fairing that protects it during ascent. Events that took place in preparation for today's launch began on January 7th when the satellite was encapsulated inside the payload fairing. On January 12th, the encapsulated payload was transported to the Vertical Integration Facility, or VIF, at Space Launch Complex 41, where it was mated to the Atlas V rocket. This activity completes the stack and is the last major processing milestone before final launch preparations begin. The launch countdown begins with moving the rocket from the VIF to the pad. The quarter-mile trip began using 6 components to complete the 20-minute trip. Weighing in at about 2 million pounds, the Mobile Launch Platform, or MLP, supports the rocket and contains air conditioning, electrical, and commodities, while the undercarriages bear the weight of the MLP and the rocket. 2 rail cars lead the move, with the payload van providing communication to the payload, while the ground van houses the ground support for the rocket. At the rear of the convoy, the Portable Environmental Control System provides air conditioning to the payload and the rocket. Finally, trackmobiles provide the power to move the 3.5 million pound convoy. The Atlas V rocket stands 188 feet tall, or about 19 stories, and weighs more than 750,000 pounds fully fueled. The RD-180 main engine produces more than 860,000 pounds of thrust to lift the rocket off the pad and begin its journey to orbit. As I mentioned earlier, the Atlas V is launching the 3rd dedicated satellite in the space-based infrared system. SBIRS, one of the nation's highest priority space programs, is designed to provide global, persistent, and tactical infrared surveillance capabilities to meet 21st century demands in missile warning and defense, technical intelligence, and battlespace awareness. The system architecture consists of legacy defense support program satellites, hosted SBIRS sensor payloads in highly elliptical orbit, and dedicated SBIRS geosynchronous Earth orbiting satellites. The satellite constellation is supported by ground infrastructure, which receives, processes, and delivers the infrared information to key decision makers. Lockheed Martin is the prime contractor for the program, with Northrop Grumman servicing as the primary payload provider. The SBIRS team is led by the Remote Sensing Systems Directorate at the U.S. Air Force Space and Missile Systems Center and is operated by the Air Force Space Command. The artwork on the payload fairing of the rocket features a black background representing the darkness of space behind an eagle, which signifies the Remote Sensing Systems Directorate. The globe represents the importance of this satellite providing missile warning, which is the cornerstone of deterrence to the U.S. and its allies. Adopting the motto from the 2 previous SBIRS launches, Always Vigilant, Flight 3 logo reads Semper Vigilans, a tribute to the SBIRS heritage. Yesterday we asked our Twitter followers to send in their rocket and spacecraft questions. Thanks to everyone for submitting some great questions. A few of you had similar questions, so I'd like to take the time now to answer a few of those, and then right before spacecraft separation, Lieutenant Walton and I will answer a few others. Many of you asked about the white vapor coming from the rocket while it's on the pad. The Atlas booster with liquid oxygen and Centaur upper stage with liquid oxygen and liquid hydrogen utilize cryogenic propellants. As we load the tanks and finish our other countdown operations, some of those propellants boil off and have to be vented out of the tank to maintain tank pressures. The white vapor is those gases being vented overboard. Others wondered about the fire that can be seen at the base of the rocket. During ascent, the aft end of the booster is subjected to high temperatures due to its proximity to the engine exhaust gases and recirculation of the exhaust plume. There is thermal protection on the heat shield to ensure that the vehicle is protected from those environments. The close-up views that show the heat at the base of the rocket is an expected part of ascent and how the heat is dissipated by the thermal protection. Finally, several people asked about 401, the Atlas V configuration we're using today. The 4 in the 401 refers to the size of the payload fairing, which today is 4 meters in diameter. The 0 refers to the number of solid rocket boosters. Solid rocket boosters provide extra thrust at liftoff for heavier payloads or when we need additional speed. However, today's mission doesn't require that extra power. The 1 refers to the number of engines on the Centaur's second stage. For today's flight, we have a single engine on the Centaur. This is Atlas Mission Control at T-minus 4 minutes and holding. We remain in the planned 30-minute built-in hold as preparations for the launch continue. In a few moments, launch conductor Ed Kidda will pull the launch team for the final go to pick up the countdown. 27 engineers and managers will be pulled for system status and the readiness to proceed with the launch. This is a final status check before launch for all Atlas vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The readiness pull includes hydraulics, pad water deluge system, electrical systems, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as launch conductor Ed Kidda performs a final pulling of the team.
Status check to proceed with terminal count. Atlas systems, propulsion.
Go.
Hydraulics.
Go.
Pneumatics.
Go.
LO2.
Go.
Water.
Go.
Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2.
Go.
LH2.
Go.
Has gas.
Go.
Electrical systems, airborne.
Go.
Ground.
Go.
Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
COM.
Go.
Timer.
Go.
GC cube.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Op safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
BSC is go.
Anomaly chief.
AC is go.
Range and weather.
Clear to proceed.
Launch director.
Launch director is go, and the launch vehicle is ready to launch.
Mission director.
This is the MD. You have permission to launch.
Proceeding with the count. T0 is planned for 0042. Set count to start at 0038 Zulu.
Roger. T0 is set for 0042 Zulu. Count will start at 0038 Zulu.
Polling is complete and the launch team has been given the go for launch. From T-minus 4 minutes until launch, you'll be listening to launch conductor Ed Kidda and his team performing the final steps in the countdown procedure. You will hear the team call out that Atlas LO2 topping has been secured, followed by about a minute later by the call out for transferring the Atlas and Centaur stages from ground facility power to internal battery power. At T-minus 155, the team will command the launch sequencer to start, followed shortly by securing the Centaur LH2 and LO2 topping activity. At T-minus 140, the team will command the flight control system to launch enable and arm the flight termination system. In the final minute, the Atlas tanks will be verified at flight pressures, followed by verification of the Centaur tank pressures. A final check of the Atlas, Centaur, and SBIRS GEO Flight 3 readiness is conducted at T-minus 25 seconds. At T-minus 3 seconds, the RD-180 engine will roar to life. After liftoff, you'll hear the voice of Rob Gannon providing launch vehicle ascent data. This is Atlas Mission Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
4 minutes and counting. 3, 2, 1, mark.
3 minutes, 55 seconds.
Ground power was enabled.
The countdown clock is resumed and we are go for launch at 7:42 p.m. Eastern Time.
T-minus 3 minutes.
Securing LO2 topping.
Atlas tanks to flight pressure.
2 minutes, 50 seconds.
FTS internal.
One minute, 59.
Vehicle internal.
155.
Launch sequencer start.
150.
Securing Centaur LH2.
Securing Centaur locks.
140.
Launch enabled.
137.
FTS armed.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and the Eastern Range are go for launch.
120.
OCU's armed.
FCS count started.
115. 110.
Vent valves locked.
T-minus 1 minute.
T-minus 1 minute.
.40 seconds.
Stable at step 3.
28. 25.
Status check.
Go Atlas.
Go Centaur. Go SBIRS.
T-minus
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of the United Launch Alliance Atlas V rocket carrying the third space-based infrared system for the United States Air Force.
And we start a closed loop control on Atlas PU. Engine continues to operate normally.
You are hearing the voice of Rob Gannon providing launch vehicle ascent data.
30 seconds into the mission, everything looks good. Engine continues to operate at 100% thrust. Vehicle is flying right down the center of the range track. And seeing normal control on the PU system. Good engine operating pressures. And we're seeing expected disturbances in flight control for atmospheric flight. Everything looks good. Coming up on Mach 1 in 10 seconds. And we're continuing to fly right down the center of the range track. And the vehicle is now supersonic. Everything is looking good. We are 7.8 miles in altitude, 3.6 miles downrange, traveling at 1,700 miles per hour. And we've throttled down to 95% right on time. And we are venting the Centaur LH2 tank as expected. Levels look good. Engine continues to operate as expected. Passing through 2 minutes into the mission, everything looks good. And we are now 50% of our liftoff weight. .150 seconds in, everything looks good. Engine continues to operate percent thrust as expected. And we followed the RCS power valve, pressurizing the reaction control system on the second stage. That booster continues to operate normally. Seeing good engine pressures. Continuing to fly right down the center of the range track. 31 miles in altitude, 50 miles downrange, traveling at 5,100 miles per hour. And we're going to close loop steering. We've throttled down to 92%, right on time. And vehicle continues to actively steer. Good engine pressures at 92%. And the vehicle now weighs 25% of what it did at liftoff. And we're now flying a constant 5G throttle segment. Everything looks good. Coming up on BECO and staging. Less than 10 seconds away from BECO. We have booster engine cutoff. Normal shutdown. And we have stage separation. And boost phase chill was accomplished as expected. Pre-start on locks and fuel. Everything looks good. Ignition, full thrust. The L10 is up to full thrust. Everything looking good. Coming up on fairing separation. And we have fairing separation right on time. And Centaur continues to operate as expected. 100 miles in altitude, 304 miles downrange, traveling at 16,000 miles per hour. Correction, 11,000 miles per hour. Thrusters and thruster loop. We're seeing very good steady-state operating pressures on the main engine.
This is Atlas Mission Control at T plus 5 minutes, 29 seconds. Rob Gannon just confirmed the successful completion of the early phase of today's flight, and all systems continue to operate nominally. The mission is currently in the first of 2 Centaur engine burns. Our next event, Centaur main engine cutoff, will occur in approximately 10 minutes. I'm now joined by First Lieutenant Nick Walton from the United States Air Force. Lieutenant, thank you so much for joining me today.
Thanks for having me. I'm so excited to be here.
We just experienced a very exciting liftoff. I know we've been waiting for that.
Right.
So can you start off by telling our audience a little bit about SBIRS and how that fits into the Air Force's space portfolio?
Absolutely. So SBIRS, or Space-Based Infrared System, is led by Colonel Dennis Bythewood and is part of the Remote Sensing Systems Directorate out of Los Angeles Air Force Base's Space and Missile Systems Center. The GEO payload has 2 different sensors on it. One is a scanner and one is a step starer. The scanning sensor scans the globe 24/7 and provides global strategic missile warning. It also contributes to our theater coverage and our intelligence missions. The step stare, with its highly accurate and agile pointing system, contributes more to our theater coverage and then our intelligence areas of revisit due to its high accuracy and fast sensitivity.
Great. It's got a lot going on. Very
Definitely.
Interesting satellite system. So in terms of the SBIRS satellite, can you tell us how that fits into the missile warning constellation that the Air Force has?
Sure. So we talked about SBIRS GEO, and we also have a hosted payload in a highly elliptical or Molniya orbit. This SBIRS GEO payload is very similar to the GEO scanner, except for the pointing of the sensor is actually performed by slewing the entire sensor on a gimbal. So it's pretty cool. We have SBIRS GEO, we have SBIRS GEO, and then the SBIRS system actually is replacing the Legacy Defense Support Program, or DSP.
Wow. So we talked a lot about what happens in space with the SBIRS satellite and the constellation. What about our troops on the front lines? How does this system affect them?
Definitely, and that's a great question, Andrew, because that's really why we're here, right, is to try and protect our guys downrange and support our troops. So with this current global threat environment, the variety, velocity, and volatility of threats that we're seeing is just greater than ever, and that's for America and our allies. And so as these threats continue to evolve, the ability to be able to reliably, persistently, and accurately not only detect missile launches, but then to provide early warning to the people that could be in harm's way is invaluable. And SBIRS really delivers that capability to meet those 21st century demands in early warning.
That means a lot to me, especially because I have a lot of friends in the military, and so it's great to hear that we're trying to send them home safe and sound to their families and friends.
Absolutely.
Great. So, like I said before, the launch was very, very exciting. But
Yes.
Can you tell me a little bit about the excitement that you're feeling as we get closer to spacecraft separation?
This is amazing. I mean, it's just to be at Cape Canaveral is just like a dream come true. But this is still just the beginning of the process that we have to go through. After we complete the launch today, we'll be in a geosynchronous transfer orbit. We still have to complete liquid apogee engine burns to circularize our orbit to get all the way out 22,000 miles to geosynchronous orbit. Once we're out in GEO, we're going to perform a couple deployments, and that'll be our solar arrays to generate power, some antennas to talk to the Earth, and then we also have a deployable light shade that comes out to shield our payload from the sun. And that's not it. So once we do all these deployments, then we have to start calibrating the payload and doing that type of stuff.
Great. So there's a lot of work to do in terms
Right.
of getting it set up. But once the satellite actually becomes operational, how do you get that capability to enter into service?
So that's a good question, and it's actually I'm going to throw a shout out to at Link256, who I think submitted a similar question on Twitter. So once we go to our operational orbital slot, then we finish basically calibrating our payload. We'll go into operations, and we'll basically have early data within about 2 months, and then we should be in full ops in as early as 7.5 months.
Wow, it's amazing that it comes around that quickly.
Definitely. We've really been trying to whittle away at how long it takes us to get these things into full operations to get the most bang for our buck.
That's great. So my last question for you before we get back to the launch, can you tell me a little bit about what you do on the SBIRS program?
Sure. Yeah, so I'm the GEO Transition Operations Program Manager. So essentially, I'm responsible to have a seamless transition from launch all the way into operations. So most of my time is spent coordinating the efforts between the contractor, the operators, and to make sure that really at the end of the day, the warfighter gets what they need.
Right. Well, that's great. I've sure learned a lot through our conversation, and we're going to have the lieutenant back in just a little bit, but let's get back to our mission.
In the telemetry system, minimal dropout in data. Engine parameters look good. Still nice and smooth. Five minutes to MECO 1. (210 miles in altitude, 1,450 miles downrange, traveling at 13,600 miles per hour. And we see Centaur PU correcting out, looking good. PU mass area coming down to around 0, and we're off the stop. Everything looks good. We are seeing the expected change in engine operating parameters as we change the mixture ratio on the engine. Four minutes to MECO 1. Centaur PU is in active control. And flight control disturbances are right as expected. Very smooth. (1,800 miles downrange, traveling at 14,700 miles per hour.
This is Atlas Mission Control at T plus 12 minutes 32 seconds into the third SBIRS GEO Flight. The Atlas, Centaur second stage, and SBIRS GEO Flight 3 satellite are currently located over the Atlantic Ocean east of Antigua. Our next event, the first Centaur main engine cutoff, or MECO 1, is scheduled to take place in about 3 minutes. Once again, here's Rob Gannon.
Engines operating right at the expected steady state levels. We see the thermal conditioning firings on the reaction control system have brought all loop temps to essentially the bottle temperature as expected. We're seeing minimal requirements for roll control on the RCS system. Two minutes to MECO 1. Centaur PU continues to control nominally. Bus battery voltages are steady, right as expected. We're continuing to see very good telemetry data. And engine pressures are shifting as expected as we change MR due to PU control. One minute to MECO 1. Following MECO 1, we will have a 9.5-minute coast duration to the second burn. Second burn nominally will last 3 minutes, 40 seconds. We will then have a little over a 15-minute coast duration to spacecraft separation. We're inside of 30 seconds to MECO 1. Continuing to see very good performance out of Centaur. 10 seconds to a nominal MECO 1. And we have cutoff. Normal shutdown within a couple seconds of our nominal timeline. 4S engines are on. And venting propellant tanks as expected. And IIP has vanished. And we've begun our turn to MES 2 attitude.
While we wait for our next mission event, restart of the Centaur engine, let's take a look at this video from Lockheed Martin on the SBIRS satellite.
SBIRS stands for Space-Based Infrared System, so it's a constellation of satellites that basically detect and track missile launches across the world.
You know, SBIRS worldwide is always there. It's a persistent infrared detection, looking for missile launches to protect our troops in the field and to protect the homeland. And, you know, when you go home and you go to a wedding and you talk about, hey, what do you do? It's like, well, I'm protecting us right now. It's pretty cool.
In the subcontract organization, we are able to be excited about and involved in each phase. So we're not limited to one piece. We get to be involved in each phase through completion and through the end of the life of that hardware.
So working out of the chief engineer's office, I get the opportunity to work in all phases. That's design, assembly, /build, test, integration, and a little bit of flight. And my focus is anomaly investigation and resolution.
As a system test engineer, one of my job functions is to ensure that flight software correctly computes and issue appropriate commands to thrusters and reaction wheels to correctly orient the spacecraft and maintain correct position in the orbit.
The things that get me really excited are getting to see the things that we actually build and work on. So a lot of the tours, going to see some of our operational facilities in Colorado, where we actually fly the satellites from. That's always exciting. Getting to see the satellites in the high bay is always a highlight.
I get great satisfaction in working with our suppliers, our internal Lockheed folks, our aerospace community, and our customer community. I find that every challenge that we face is it's a team effort, and that brings the biggest joy for me.
One of the most interesting part of being a system test engineer is that you get to work with the vehicle from the beginning to the end. So you actually get to watch the vehicle take shape from the beginning, which is just a shell, to the end, which is the final product.
Yes, designing things for space is a own unique challenge. You have the radiation environment, you have the extreme thermal environment, all that stuff. From my perspective, though, the thing that's most challenging is you have to get it right the first time.
The challenge from a subcontract management perspective comes to ensuring that all of the hardware is built correctly, tested correctly, and is going to function correctly in space. You can't go up into space and fix your hardware if something breaks.
So I'll be working the launch room here in Sunnyvale in our flight operations support facility. For the first month or so, we have what's called launch and early on-orbit test, which is basically check out of all the basic functionality of the satellite, ensuring it's safe and working properly. As part of that, we do 24/7 shift coverage on 3 8-hour rotating shifts.
So launches are an interesting point in the program. They're the culmination of a whole lot of effort, and they're also the beginning of the life of that satellite on orbit. They're exciting because all this work leading up to this one moment, and it goes, and then they're also bittersweet because now everything that you worked on, all the hardware you delivered, all the teammates that you worked with, it's now off the ground and gone.
They get to the end and you can see that smoke coming at the bottom and it blasts off and you get goosebumps and chills and you're so excited about the fact that you had a part in making this happen.
Four minutes to MES2.
This is Atlas Mission Control at T plus 22 minutes. We're a few minutes away from restart of the Centaur main engine. Let's go back to Rob Gannon.
And we've terminated the PTC roll. Continue to maneuver the vehicle in preparation for MES. As we approach main engine start 2, we will be increasing pressures in the propellant tanks. We will then conduct a 23-second LH2 pre-start, followed by 9 seconds of clock's trickle chill, which will switch over to full flow chill at 4 seconds prior to engine start. Inside of 2 minutes to MES. And we're pressurizing propellant tanks. Inside of 1 minute to MES2. Restart sequence continues to execute normally. We're going to the start position on Centaur PU. LH2 pre-start. Inlet valve is open. Tank housing temperature is dropping. Clock's pre-start right on time. Bypass closed. Ignition, full thrust. RL-10 is up and running normally. This will be a approximate 3-minute, 40-second burn duration. PU has been enabled. And everything is looking good.
As Rob Gannon just reported, the Centaur main engine has been restarted for the second of 2 Centaur engine burns. This burn will last approximately 3 minutes. The Atlas V continues to travel in a southeasterly direction. Following our next event, MECO 2, or cutoff of the Centaur RL-10 engine, the Atlas V will cross over the African continent, where the trajectory will switch to an easterly heading. Separation of the SBIRS GEO Flight 3 satellite will occur over the Indian Ocean, east of Madagascar. Listen in as Rob Gannon reports the next mark event.
Everything looks good. Good at steady state operating pressures. Tank pressures look good. Bottle pressure looks good. Minimal roll control is being required during the burn. And 2 minutes to MECO 2. Second burn continues to execute normally. Engine pressures look good, PU looks good. The other vehicle systems right as expected. One minute to MECO 2. Vehicle is performing right as expected. "30 seconds to MECO 2. Engine pressures are nice and steady. 20 seconds. "10 seconds to MECO 2. Cutoff. We have MECO 2 slightly early, indicating both nominal performing second stage. 4S engines are on. Engine is beginning to maneuver. Reorient to SEP attitude. We're starting up a PTC roll of -1 degree per second. And this will be a 15-minute to 12-second coast to spacecraft separation.
As Rob Gannon just reported, we've received MECO 2. We just accomplished MECO 2.
Yep.
And I have the lieutenant back with me here today, so I'm going to ask you a couple more questions if that's all right with you.
All right, yeah, that sounds good.
So earlier in our interview, we talked a little bit about the military capability of the SBIRS satellite.
Right.
Can you tell me a little bit about if there's any sort of civilian utility?
Definitely. Yeah, so actually in the Remote Sensing Systems Directorate, we've been striving to get the most capability that we can out of our system, and that includes civilian capabilities as well. We actually just found out the National Forest Service can use our data to help them find hotspots in forest fires, so that way they can concentrate their resources to put those fires out a little bit faster. So that's a pretty cool capability that we didn't realize we had before. And then we also just recently opened up an exploitation lab in Colorado, and that's so that we can get universities and other mission partners involved. They can look at our data and see what new and innovative uses they can get out of it.
That's great. I really like that not only are we helping everyone through forest fires,
right,
but we're also engaging the younger, college students to get inspired by space and things
right,
like that. So that's great to see that there's more civilian utility than I had originally thought.
I know. As many new uses as we can get, the most bang for the buck is really the best stewards of tax dollars, right?
Right. So I can definitely tell your passion about the SBIRS program. Can you tell me what actually drove you to be in the Air Force?
Sure. So I knew from a young age that I had a passion for design and engineering. And in high school, I joined an organization called the Civil Air Patrol, which is the United States Air Force Auxiliary. In that organization, I really found a passion for leadership, and I knew that I had an interest in aviation. So that motivated me to go to school at Embry-Riddle Aeronautical University in Arizona. I graduated there with a Bachelor's of Science in Aerospace Engineering, and upon graduation, I was lucky enough to receive my commission as a second lieutenant in the United States Air Force. And ever since I've been on active duty, it's been an absolute blast.
That's amazing. Well, congratulations on all you've accomplished.
Thank you.
And also, I think engineering is very exciting, so good work on that as well.
Thank you.
I think engineers are pretty cool.
They are.
All right, so we're going to switch up our broadcast just a bit, and we are going to answer those Twitter questions that our followers
That's
had.
right.
Do you want to get started?
Sure, it sounds great.
All right, great. I'm going to ask you the first question.
Okay.
All right, the first question is from Zach S09. How many SBIRS GEO satellites will be flown to geosynchronous orbit?
Well, we are lucky enough to just have seen the third flight of SBIRS GEO today, but we do have a SBIRS GEO Flight 4 that is tentatively scheduled to be launched later this year, actually, in November.
Wow.
I know, it's a pretty fast turnaround. And then we also have SBIRS GEO Flight 5 and 6 that are tentatively scheduled out in 2021 and 2022.
Oh, great. I can't wait to see all those happen.
Definitely. I hope we're right back here.
Me too.
All right, so I think I have the next question for you. At Timmy C2112 asks, congrats on the launch. Are there any 3D printed parts on the rocket?
Well, thanks, Timmy C, on the launch. So far, so good. I love this question because 3D printing is what I do.
That's right.
Yeah,
oh,
exactly.
Yeah, wow.
Yeah. So right now we do have 3D printed parts on the rocket. I, helped put the design together and test the materials and things like that. So we have a material called Ultim 9085, which is a polymer, and we're flying it on the environmental control system, which keeps our hot avionics cool so that they continue, to move the rocket in a way that we want it to. So we have quite a few parts that we've done with that using fused deposition modeling, which is a type of 3D printing. But my favorite thing is because I'm a metallurgist, we're actually going into printing with metallics using a material called Inconel 718, which is a nickel-based superalloy. But we are going into testing for that right now. We're actually going to start in just a couple weeks, and we've identified parts. So by the end of this year, we will have metal parts that are being printed to put on the rocket. So
That's
I'm really
incredible.
excited.
Wow, yeah, I bet. I mean, I never knew that you had that capability with metal. That's really cool.
I know, it's amazing the things that we can do now.
Absolutely.
All right, so what's the next question here?
Let's see.
At Base Runner 0723, is SBIRS going to be used by NORAD?
So that's another great question. So SBIRS, the data from SBIRS, the missile warning and surveillance data, is actually fed to the President, Secretary of Defense, combatant commanders, the intelligence community, and then other key decision makers as well. And then NORAD is the North American Aerospace Defense Command, and that's actually a bilateral organization that involves Canada and United States. And so the Canadian Prime Minister and the United States President get together and they're briefed by NORAD. So yes, the President gets this SBIRS information to NORAD.
That's really interesting that you mentioned the President on today of all days for the inauguration.
Right, of course,
yeah,
Inauguration Day.
There we go. Very American today.
Definitely. All right, I think I have the next question for you.
All right, let's see.
So let's see. At Nate Dog 1.
Great
Great
name.
handle. There you go. While the engines are burning, is there electricity being produced from them?
So the answer to that is no, not using our current engines that we have right now with the RD-180 and the RL-10. However, we are designing a brand new rocket, and on the upper stage, we're designing something called Integrated Vehicle Fluids, IVF for short. What that's going to do is provide us with electricity and power up in space for a long duration. And that's going to be similar to an auxiliary unit that you'd have on like a jet airplane or something like that.
Okay, right.
Yeah, so eventually we will have that type of capability, but right now we don't.
Interesting.
Yeah. So I think next question?
Yeah. So let's see. At Philip Turtles 1 asks, what pad activities usually occur after launch?
You know, that's an interesting question because I feel like most people get mostly excited about the liftoff and not so much after.
Everyone goes home, right?
Yeah, exactly. I wish it was like that. But there's actually quite a bit of work that needs to be done once we do launch off the pad. So a team goes in and assesses any type of damage that may have happened while we're on the pad. And then if anything does need to be refurbished or changed out, we'll go ahead and have a team over the next couple days or weeks go ahead and fix it all up so that we're ready to launch. And we can do that pretty quickly. We've had very short duration launches or, you know, short time in between each of the launches before. So we have that capability. Another really interesting thing is that we have photographs that you've seen on Instagram and Twitter of the rocket really close up. Well, photographers go in and actually set up their cameras around the rocket. And so you get those nice visuals. So after the launch, they go in and pick those up so you can tweet them on Twitter and show everybody the amazing launch. So.
All right, I think we have one last one. At Rye O'Connor asked, what are the towers on the perimeter surrounding the rocket? And that's a really cool question, too, for me, because when I first came here, I had no idea what that was about. So you want to explain that?
Yeah, absolutely. So those are a part of a lightning catenary system, which what that means is basically while the launch pad is out, while the rocket is out on the launch pad, if it starts to lightning or anything like that, that catenary system will actually, take the lightning so that our vehicle isn't damaged at all, because we do build it so it can stay out on the pad and all that kind of stuff. So.
Sure, for winds and that stuff, but I don't think we want to get struck by lightning.
Nope.
So there you go. That's what the system's for.
So it takes all that, and
we're
prepared for anything.
Good to know.
Yep. All right, so I think that's all the questions that we have time for to get answered. But thank you, Twitter followers. You did a great job asking some great questions. We're going to return to flight in just a minute. But before we turn to the flight, let's take a look at some of the great launches that we have scheduled for 2016. We have a very full manifest. We have 7 more national security missions, 2 science missions, and 1 International Space Station resupply mission. So it's going to be a really exciting year. 2017. Sorry. The whole new year thing is really...
The first launch of the new year.
The first launch of the new year.
There you go.
Yep.
And the vehicle is just coming over the horizon to the reef tracking station. 5.5 minutes to spacecraft separation. 2,300 seconds into the mission. Everything is looking good. 4 minutes to spacecraft separation. Three minutes spacecraft separation. 50 seconds into the mission. Vehicle continues to coast as expected. Rates are right as expected. Electrical systems look good. RCS activities as expected. Everything is looking good for spacecraft up.
This is Atlas Mission Control at T plus 41 minutes 26 seconds. We're a few minutes away from spacecraft separation. Let's go back to Rob Gannon for our final call of the evening.
Two minutes to spacecraft separation. And we're now coming out of the PTC roll. Roll rate has nulled out. And we've begun our solar vector roll right on time. Inside of 1 minute to spacecraft separation. "30 seconds to spacecraft separation." We've completed the solar vector roll. Next event we're looking for is spinning up to 1 degree per second for spacecraft separation. And we've begun spin up. Coming up on spacecraft separation. We have spacecraft separation. Both brake wires indicate a good separation. Vehicle is de-spinning from its PTC roll. And vehicle started to turn to CCAM.
This is Atlas Mission Control at 44 minutes, T plus 44 minutes, 30 seconds. Congratulations to the entire launch team throughout the nation on a successful flight, and congratulations to you, Lieutenant.
Thank you so much, Andrea. It's an absolute blast to be here.
Literally.
There you go. That's such a significant milestone in the SBIRS program, and I'm really looking forward to having the rest of a successful mission with all the other things we have to do.
Me
but
too.
Thanks again for having me here.
Oh, and thanks so much for being here. It's been a blast.
Definitely.
I said it again. All right. Well, if you want more, and special thanks to Rob Gannon for his excellent commentary on today's launch. I also want to let you all know that if you're interested in learning more information about the Atlas V and United Launch Alliance, you can go ahead and visit ulalaunch.com. You can also follow us on Twitter and Instagram for more information. Before we complete our live coverage for today, let's take another look at today's liftoff, which occurred at 7:42 p.m. Eastern Time. I'm Andrea Lenhoff, and on behalf of the entire launch team, thank you for joining us and have a great night. And liftoff of the United Launch Alliance Atlas V rocket carrying the third space-based infrared system for the United States Air Force.
MLP. And we start a closed loop control on Atlas PU. Engine continues to operate normally.
You are hearing the voice of Rob Gannon providing launch vehicle ascent data.
30 seconds into the mission, everything looks good. Engine continues to operate at 100% thrust.